right, everyone, starting section 3.1, rates of change. There are a couple of different kinds of rates of change that we'll talk about today. One of them is the average rate of change, and the other is instantaneous rate of change. So for average rate of change, let's say that we have a function f of x graphed right here, and I know 2 points on the graph of f of x, specifically when x is equal to a and when x is equal to b. We can let a be kind of like the starting point and b be the final point. So if I were to look at the line that connects my start to my finish, right, this is an example of what we call a secant line. Right, and it passes through 2 points on the curve and kind of cuts through it like the purple line drawn in the graph. To find the average rate of change, we actually need to find the slope of the secant line. So that's going to be change in y over change in x. Final y minus initial y over final x minus initial x. So if I look at my graph, my final y value is f of b. My initial y value is f of a. So that's my change in y. My final x was b, my initial x was a, so that's my change in x. And for a little bit of context, we could think about it as, let's say f of x models my position along a highway, right? F of a would be my starting position, f of b would be my ending position. So f of b minus f of a, that's my change in y, would actually be my displacement. And b minus a would be the change in time. And if I take change in position or displacement divided by change in time, that gives me velocity. Right? And a little note on units, if the units of f of x are in miles and the units of x are in hours, then the average rate of change would have units of miles per hour. Right? It's always units of y per units of x. And that's true for any rate of change, be it average or instantaneous. So our average rate of change, just the slope of the secant line, the slope of a line that we know 2 points on, change in y or change in x. Now the tangent line, well, getting ahead of myself. Now the instantaneous rate of change is actually a little different. So if you can look at the function here, I only have one line drawn on there that passes through only 1 point on the graph of f of x. So it kind of sideswipes the graph at 1 point. It doesn't actually cut through the graph near the point where x is equal to b. This is an example of something called a, change color, tangent line. Or the line tangent to the graph of the function f of x. And for this, imagine that we had our secant line from earlier drawn through that point. Right? If I were to take it so that a gets closer and closer to b, there we go. Oh, nope. Okay, snap in there. All right. If I were to draw it so that a gets closer and closer to b, we would see that the secant line starts to look more and more and more like the tangent line. Because to find the slope of the tangent line, if you think about it, we don't actually know 2 points, so we can't use change in y over change in x. Instead, we actually have to use the fact that the tangent line is a limit of the secant line. So if I wanted to write out the slope of the instantaneous rate of change, or the slope of the tangent line, that would actually be the limit. You could think about it as a, whoops, that's an a approaches b, of f of b minus f of a over b minus a. That's one way you could write it. The way that we typically see this written, though, is actually the limit as delta x, so the change in x, which we're going to call h, approaches 0, of f of x plus h minus f of x all over h. So here we're kind of thinking about it as to get to the point x equals b, I need to add some change in x to my starting point. If we let x represent the starting point, then this is just exactly what we did with secant line. It's just a limit of that slope. So other notes about this. What I've just written out here is what we call the definition of a derivative. So the derivative is a limit, specifically the limit of the slope of a line. The limit of the average rate of change as the two endpoints get closer to each other. There are several different ways you could think about it, but ultimately this is the definition that we're working with, which is important because definitions are important. In math, a lot of times those are the starting points for a lot of problems. So let's look at a couple examples where we have a function rule and we want to find each different type of rate. So first example, we're given a function f of x. We want to find the average rate of change on an interval. So my first step is to figure out the y values at my endpoints. So we're going to start by evaluating f of 1. I'm going to get 1 squared minus 3. Then evaluate f of 0. I'm going to get 0 squared minus 3. And then I can use my definition for the average rate of change. It's just my change in y over my change in x. So to evaluate these, this becomes -2. This is equivalent to -3. So my average rate of change is going to be final y, -2, minus initial y, -3, divided by final x, 1, minus initial x, 0. And if I do a little bit of computation, we find that this is equal to +1. All right, 2 minus a negative, so -2 plus 3 gives me 1, divided by 1 gives me the answer. And that's the average rate of change for that function on that interval. Next example, let's say we want to find the instantaneous rate of change of the same function at the value where x is equal to 1. So we could use a lot of different representations of that limit definition. Right, so let's think about it as the limit as x approaches 1 of f of x plus h. Oh, whoops. My bad. We want the limit as h approaches 0. It's always h approaches 0 for this. We never write the limit. And I mean, we could write the limit in terms of x in some circumstances, but I'd rather show you what it looks like with h, because that's typically what your textbook is going to show you. So the limit is h approaches 0 of f of x plus h, but we know that x is 1 for this problem, minus f of 1 divided by h. So at this point, just remember how function notation works, right? If I want f of something, I have to substitute that something for the x. So we'll have the limit as h approaches 0 of 1 plus h squared minus 3 minus f of 1. So if I were to find f of 1, I would just need to plug 1 in for x. 1 squared minus 3, I get -2. Then we're going to divide that by h. So at first glance, we'll end up noticing that plugging in 0 for h results in 0 over 0, which means we need to do some algebra. The only algebra that I see we can do here is to actually expand 1 plus h squared. So I'm going to do that in a different color here. So 1 plus h squared is just 1 plus h times itself. So that'll be 1, which I get from doing 1 times 1, plus 2h, so it'll be 1 times h plus h times 1, plus h squared, which is h times h. I wrote this in a different color. Notice I did not put any continuing equal signs here because that's side scratch work. All right, but anyway, going back to our limit, we have the limit as h approaches 0 of 1 plus 2h plus h squared minus 3 minus a negative 2 gives me minus 1 over h. And then what I notice is that my 1's are going to subtract, leave behind 0. And then from what I have left, I can actually factor out an h in the numerator, because both of the terms have an h. Then I notice I have a factor of h in the numerator and in the denominator, so we can divide that. I'll leave behind a 1, and now we just have the limit of 2 plus h. Well, if I plug 0 in for h, now I just get 2. So that's my instantaneous rate of change, or the slope of my tangent line for this function at x equals 1. So now some generalizations. So the instantaneous rate of change can be computed like we did in that last example, but if we get our answer in terms of x, it actually gives us a way to find instantaneous rate of change for the same function for any value of x. And generally when people say the derivative of a function, that's what they mean. It's a formula that gives me the instantaneous rate of change, or the slope of the tangent line, at any value of x. So let's look at this last example. Find the derivative of f of x equals x squared. So we can go back to our definition. We know that the derivative is just the limit as h approaches 0 of f of x plus h. We don't have any particular x value to use now, minus f of x all over h. So if my function is f of x equals x squared, then f of x plus h is just going to be x plus h squared. So if the limit is h approaches 0 of x plus h squared minus our f of x, which was just x squared, all over h. So if I do the algebra like I did last time, right, when we expand x plus h squared, we're going to end up getting x squared plus 2xh plus h squared. And remember, we're still subtracting the x squared and we're still dividing the whole thing by h. So then, kind of like last time, we see that the x squareds are going to subtract and leave behind 0. And then what's left, we can factor an h out in the numerator because both terms have an h. So we have the limit as h approaches 0 of h times 2x plus h divided by h. So then I notice that I have a factor of h in the top and in the bottom. So those will divide, they'll leave behind a multiplying 1, which does nothing. And h approaches 0. If I substitute 0 in for h, I'm left with 2x. So that is the derivative of x squared, 2x. And to kind of illustrate the idea I was talking about earlier, I could pick any value of x that I want. I've drawn the graph of y equals x squared over here. I could pick any value of x that I want, and whatever that value of x is, 2 times that gives me the slope of the tangent line. So for example, when x is 0, 2x would also be 0. And if I were to draw the tangent line, it would be horizontal. Similar thing, if I plug 1 in for x, then I get 2. When x is equal to 1, if I were to draw this tangent line nice and steady, I would find that I get a line that has a slope of 2. That wasn't a very good job. Whoops. But anyway, no matter what value of x I plug in, as long as that is inside the domain of f of x, I'll be able to figure out the slope of the tangent line, or the instantaneous rate of change. So to summarize, we talked about 2 different kinds of rates today. We had average rate of change, which is the slope of the secant line. For that, we know 2 points, a final point and an initial point, and we can calculate the average rate of change by getting the change in y over the change in x, final minus initial for both. The other rate was the instantaneous rate of change, which is a limit of the average rate of change. The instantaneous rate of change is also known as the derivative, and is the slope of the tangent line, which is similar to the secant line, but only passes through 1 point on the function in that immediate area. When you find the derivative formula for a function, that allows you to figure out the slope of the tangent line or the instantaneous rate of change for any value of x that you plug into the formula. And we can do that using our limit definition, which is going to be very important for you to remember. And that's all for today. Have fun.